Okay, this is joint work with Tito from INS Lyon. And actually, this is part of Tito research program. I just helped him with the geometry of interaction, but his work is part of Tito's idea on transducers and type lambda calculi. So at the beginning of computer science, there was the lambda calculus. So and then it was proved equivalent to Turing machines, to partial recursive functions, and to many different kinds of computation devices. And in particular, the canonical notion that stems out of all these mechanisms is the one of computable function. But also, since the beginning of computer science, there were also finite automata. These are very easy devices with just a finite state. And as well as the lambda calculus, also finite automata have different equivalent formalisms. For example, regular expressions, regular grammars, monadic second-order logic. I mean, somehow there is some canonicity in finite automata, and the canonical notion is the one of a regular language. So, of course, the notion of computable function is much more general than the one of regular language or regular acceptor. So there is not a clear possibility of expressing, for example, lambda calculus computations through finite automata, of course. But still, we ask ourselves, is there any connection between the higher order formalism of the lambda calculus and finite automata? And in particular, there is an old result about that. So since the lambda calculus, the untyped lambda calculus can express all computable functions, of course we have to restrict ourselves in order to capture only the regular languages. And so the typical way in which we restrict the expressivity of the lambda calculus is via types. So we introduce a simple type system with Booleans as the base types and function types. So a standard simply typed lambda calculus with Boolean as the base type. And then we're supposed to have an encoding of 0-1 strings, for example, the one by Böhm and Berarducci, but there are many. If we have this, then the types of string is the following one. And Hillebrand and Kanellakis in 96 proved that a term T is typeable with type string arrow bool if and only if the language defined by T is regular. So we can interpret a term T of this type, of course, as an acceptor of strings, and that we have these characterizations. So we have a way to obtain, again, the class of regular languages also out of the simply typed lambda calculus, which is a very canonical notion of computation. This result was actually overlooked in the literature, and I think very few people knew about this, at least before all the works by Tito. And so in this talk, I'll tell you about transducers, actually, and not automata, but transducers are just automata with output. So we have as output a string. And actually, if we want to be more precise, we will not talk about word transducers, word-to-word transducers, but tree-to-tree transducers. So the input as well as the output is a tree. But this does not make a huge difference. I mean, I won't enter inside the details of the definition of transducers, of tree transducers, because it is quite involved and technical. But I mean, if you have an intuition about word transducers, this is enough. So Tito and co-authors have put many characterizations of different kinds of transducers using different types of different kinds of lambda calculi, and in particular of linear lambda calculi. So restricting in a very ingenious way the use of exponentials in the lambda calculus, you can characterize different kinds of transducers. And this is Tito's program, which he calls implicit automata theory, as well as implicit complexity theories about characterizing through programming languages complexity classes. While here we are concentrated about transducers, automata, etc. So how does a proof of characterization work in general? First, we have to encode the chosen automata class in the selected type lambda calculus, and this is typically a programming exercise. It's not so difficult if we have chosen carefully, of course, the type of lambda calculus. But then there is the other direction, and this is way more difficult because we have to implement somehow the beta reduction of these selected lambda calculus inside automata, inside transducers. And of course, transducers are first order objects, so implementing beta reduction through them is not so easy. Because all these kind of devices, transducers, tree automata, etc., they all have a finite state, or if not finite, it's a finite state augmented with maybe a stack or maybe some pointers, but for sure they don't have rewriting properties, rewriting capabilities. So implementing beta reduction is not trivial, and even when we are in the case of linear lambda calculi or affine lambda calculi or restricted lambda calculi, still beta reduction is a complicated operation. So this is the direction. And we propose this new approach, let's say, for solving this hard direction, because and this new approach is using abstract machines, because abstract machines are already automata-like devices, and they implement beta reduction. Of course, if we have an abstract machine like the ones that Ugo presented this morning, like the Krivine abstract machine, the interaction abstract machine, these can implement the untyped lambda calculus, so these are Turing-complete formalisms, and there is no way to implement them using automata. But still, we can think about maybe some restrictions of these abstract machines that are already automata, and in particular are already the kind of automata that we want to prove equivalent to some lambda calculi. So, the Krivine abstract machine in particular does not seem parsimonious enough, because at the heart of Krivine abstract machine there are pointers, and we need to save all these pointers in the environment, in the stack, and so we need to have all this memory, and it's very difficult to think about a restriction that makes this memory finite or something like finite plus a stack. So Krivine does not seem the right tool because it needs pointers. But the interaction abstract machine that Ugo introduced this morning instead has more interesting properties, because it doesn't work with pointers. All the transitions of the interaction abstract machine are local, and so there are no jump mechanism around the syntax tree of the term. So probably we can do something with it. So it was introduced by Maki and Danos and Renier in the 90s, and it was based on the Girard geometry interaction, so it is very well founded in theory, let's say in the proof theory of linear logic, and it has a nice categorical model, so it is a canonical object somehow. And in particular, it has been used in implicit complexity theory by Dallago and Schoep, by Mazza, by Aubert and Courtos. So it has been used already many times to prove typically log space soundness and completeness results. So it has some complexity our flavor. However, as also Ugo mentioned this morning, we have proved that the interaction abstract machine is not reasonable both in time and space in general. So if we consider the untyped lambda calculus, so in the Turing-complete framework. But still, we have these positive results, and all these results in implicit complexity theory use some restrictions of the lambda calculus, and typically type systems inspired by linear logic. So let's start from the affine interaction abstract machine. So we consider an affine lambda calculus. This is a very simple object, And the machine that implements the affine lambda calculus is very, very simple. In particular, it's this machine. It's very elegant. It's symmetric. It's a reversible machine. And we have just one stack, which here we call token, following the tradition of the geometry interaction. And this token is just made by black or white dots. So it's a very, very simple stack. And if you see, all the transitions are local, so we move around the syntax tree of the term, but in a local way, so we don't have to store any pointer. We have just one fixed input term, and let's say the subterm component of the state, of course, is a pointer to this initial term. So we just need one pointer, but just one. And then we need this state to store the dots, the stack made of dots. And so this state could be arbitrarily large, but if we fix the types, if we fix the size of the types of the type derivation of the term under evaluation, then the size of the stack is limited by the maximum size of the types occurring in the type derivation. So if we fix the size of the types as a parameter, then also the size of the stack is fixed, is finite. So we can encode into a finite state all the possible configurations of this stack. So the affine YAM is reversible, transitions are local, the size of the token is bounded by the size of the types, and of course we need to traverse the syntax tree of the lambda term under evaluation to follow the computation. But this is exactly what an automaton does. And so, in particular, we can implement the affine YAM by reversible tree walking transducers. So these are a kind of automata that traverses trees, but this is exactly what we do. They have a finite state, but we have said that the stack can be represented by a finite state. So this is a very old class of tree transducers by Au and Ullmann in the 70s. So it is a canonical class of automata. And so this is our first result. But now we can go on, and we can consider a quasi-affine lambda calculus, where the quasi means that the base type is not anymore O, but it is bank O. This means that in our calculus we can duplicate base type. So we can encode. Of course, we are more expressive than before. And the interesting thing is that we can enrich our machine to cover these cases. So we have to cover with non-linearity, adding some transitions. So we have to add, of course, a way to encode non-linearity, and we add it as an explicit substitution or a let constructor, if you want. This is a non-linear let constructor. And then we also add to the language explicit bang to handle boxes. The interesting thing is that although we have added exponentials, of course in a limited way, we don't have to add an explicit stack to handle exponentials. And this is because of this restriction to the exponential only to the base type O. And so the machine is correct, this machine is correct, so it has all the transitions of before plus these 4 transitions. But as you can see, the machine is not reversible anymore. So for example, there is no the reverse transition of the bang, and also there isn't the reverse transition for the variable when this is bounded by the explicit substitution. And of course, I mean, here we couldn't go the other way around, because we don't know where to jump, because there could be more than one occurrence of x, because x here is non-linear. So if we don't save somehow the occurrence of x, we cannot go back. But still, this is not needed when we compute. So the machine is correct. is not reversible anymore, but it's still local. The size of the token is still bounded by the size of the types, and we do not need any exponential information. And so the quasi-affine interaction as a machine can be implemented by 3 working transducers. So the same class as before, but of course we have dropped the reversible property. Now, non-reversible 3 working transducer can be implemented in the almost affine lambda calculus. So this is a programming exercise, as I was saying before, but it's not easy to see that. It's not difficult to see that we can do this. And so, putting together this direction of the statement plus the 2 that we have already seen, we have a characterization theorem that says that affine lambda terms correspond to reversible 3 working transducers, while quasi-affine lambda terms correspond to 3 working transducers. So we have a neat characterization because these 2 classes of lambda terms are very natural somehow. The affine lambda calculus is very natural, and giving the possibility of copying terms of ground type is very natural too. So, and we have that augmenting the lambda calculus with these features gives rise to these characterization of 3 transducers. So, concluding, we have once again the insight that the geometry interaction, the way in which the geometry interaction evaluates lambda terms can be used as a tool to prove interesting characterization and equivalence results. So, as in the works in implicit complexity theory. And this is because of the very peculiar nature of how geometry interaction evaluates lambda terms. And moreover, we would like to go beyond this first characterization. In particular, we already have actually the result about considering bang depth 1 lambda terms. So these are terms in which we allow to have just one level of boxing, of nesting of boxes. So, but not only for terms of base type, but for any type. So, and considering this kind of lambda terms, we obtain the invisible pebble tree transducers. These are a more niche class of transducers. They were introduced something like 10 or 15 years ago in order to describe the mechanism of parsing of XML files. But then they have been used a lot in the recent years by the automata theory community. And so allowing this limitation in the exponentials give rise to this nice class. And we already have actually this result. And the proof goes again by an interaction observed machine, which still in this case is quite simple. It needs this time a layer of exponentials, because we need one exponential stack, but this exponential stack is very particular, and it can be engineered in a way that it is implemented on these pebble tree transducers, which have more than finite state. They have the possibility of having a stack of pointers. So, and for future work instead, we would like to understand if maybe we could devise something for bank depth k with k fixed. So maybe this kind of lambda terms describe a family of automata. We don't know. So thank you.
Thank you. As a question, we have time for 1 or 2 questions. Yeah.
So thanks for the talk. So I wanted to ask about the model of tree transducers, because in tree transducers, there is one way of reading trees, which is from the bottom, and one way of reading from the top, and they kind of characterize 2 different classes of languages. Yes. So what is this reversible?
Okay, yes, we read from the top.
Okay.
Yes.
Thanks. And can I ask another question? Yeah, sure. I don't know about pebble tree transducers, but pebble automaton correspond to some sort of logarithmic or sublogarithmic complexity classes. Just like the correspondence with just finite automaton, lambda calculus is implicit because it's also, you could think of it as constant space. So it's implicit complexity in that way. And so I was wondering whether this notion of sublogarithmic spaces could be useful in proving the hard direction.
Well, we have tried about another fact about pebble automata, and we weren't able to prove that, actually. Yeah. Because there were some technical difficulties, yeah, using these the fact that you are mentioning, yeah. But yes, we have looked at it.
Thank you. So thanks for the talk. So I remember some old work by Sylvain Salvati, where he was using similarly tree walking transducers to represent some kind of grammars, which he called second order string ACG, which I can't remember what it is. But I mean, from what I recall, it was very like GOI construction. It was not explicitly phrased in GOI, but it was really in the same spirit. So I don't know if you've seen that.
I haven't looked at it, but I'm almost sure that Tito did, because he read all the work by Sylvain Salvati, and so I think he read it, but I'm not sure.
And another question, if I can ask, is this ongoing and future work part reminds me of the connection between higher order pushdown automata and recursion schemes and the hierarchy of recursion schemes. So do you think there's a connection with that?
I don't know, but it would be very interesting to understand it. Since also, these are connected to higher order model checking, so yeah.
Thanks.
So let's stop now. Let's thanks again Gabriele.